Okay, this is a second example. I've chosen one from, later in the book a little bit. This one we're also going to find the Cartesian equation. And Cartesian equation is where you make the link between what y and x are doing, and there is no part of t. It directly says where x is, where y is, and puts the link in, the normal graph that we draw. Now I've already graphed this for us to compare what happens as we go through. And I'm not going to go through drawing it again. Use your calculator to build up list of points. So let's first of all start out with the domain for this function. So the domain on this function, what we need to think are what happens to the x values for the key values of t. So let's say t equals -2. We are allowing this, so if this is one of our points, it can be an equal. So this is part of the domain. It's not excluded. We put it into our value and we get x equals x minus 2, the log of -2 plus 3, which is the log of 1, which is 0. So this is suggesting that x is greater than or equal to 0. See what happens when you put in large T. So large values of T leads to a log of a large T, which is still large. So this is going off to infinity. These are the limits we're doing there. We should really do a quick check as well and make sure there's no other limits in between. So dx, dt, we're doing the differential of that, and differential of log of t plus 3. When we differentiate them, standard one is 1 over t over 3. Okay. You can do it through the chain rule. Find out can we find a value where this is going to go to 0. So this is one of our little proofs. We're going to assume that there is a point where this has a minimum or a maximum. 1 and t over 3 equals 0. No matter how you rearrange it, we wind up getting to 1 equals 0, which is impossible. So by contradiction, we've now shown that there is no minimum point. What we have to be careful of, though, is making sure we say the domain is x and 0. It is between there, and as it increases, it went up to infinity. So the x is actually greater than or equal to 0. Okay, up there. You could actually just argue that straight from the log function. Log is not defined for anything below. Actually, it's not defined for 0 either. Oh yeah, we got -2 in our values there. Okay, so that one was okay. Let's go for the range. And the range of the function, we do the same idea. We say what happens when t is -2. Well, y of -2 is going to be 1 over -2 plus 5, which is 1 over 3. So we can have a value of 1 over 3. Also see what happens for large t's. So as t goes large, as it goes to infinity, we get some number over something getting close to infinity plus 5. So this gets close to 0, but it doesn't reach it. Okay, this is a limit. Large values, we did the limit as it goes large. So we do not have 0. It's not part of my range. Also, let's do a quick check on dy dx. So where's my function? Let's take the dy dx from above. Copy it. Just I've still got it on the screen with me. Once more. most of that below, so it's still on screen for us. Let's check and see if there's a value in here where it can go. We can get another minimum as well. So we try differentiating y with respect to t. We are differentiating 1 over t of 1 over t plus 5. You can rearrange it as u equals t plus 5, du dt is 1, and therefore we are differentiating u to the minus 1. U to the minus 1 gives me minus u to the minus 2, which is minus 1 over t plus 5 all squared. What we're trying to say is, does this equal 0? So again, we're doing the proof by contradiction. So we're assuming this would be 0. Can we make this equal to 0? Well, when you multiply across, this disappears. There are no other minimum. So there's no point that it's dipping down. It's purely between these two numbers. So that leads to my range. So I'll just get this out of the way now. Keep doing that. So now I can take the range of this value as being from 0 to 1/3, y is in the middle. We are allowed to be t is minus 5 and therefore 1/3, but we're not allowed to go to 0 because it never gets to 0. And in P4, that is important. P4 must be more careful about the signs. Last part is the Cartesian equation. So we want the Cartesian equation of this function. The Cartesian equation, what we need is to find one equation in terms of t, and we can substitute it into the other one. I'm going to look at doing it with this one. I might even try doing that one as well because I think it's reasonably easy. So we need to rearrange this so t equals something. So I'm doing log by doing e to the x, and that's t plus 3. E to the x minus 3 is equal to t, and then I can substitute it into this equation. So we now get y is equal to 1 over e to the x minus 3 but plus 2. So it's equal to 1 plus 5, sorry. Jumped ahead in my head. So it's e to the x plus 2. And that's one way to get that Cartesian equation. If you get stuck with it, try the other variable. Remember, x equals is a perfectly valid form. So I could try in the blue, come on. So I'm going to try y equals 1 over t plus 5. T plus 5 equals 1 over y. Yep. So t equals 1 over y, subtract 5, and then substitute that into this function. So we can now get x equals the log of 1 over y minus 5 plus 3. We're now going to get minus 2. And if you actually realise you can do a rearrangement from this, again going to e to the x is now equal to 1 over y minus 2, which leads me to e to the x plus 2 is 1 over y, which rearranges to give me my final version again by flipping. Okay, so you do have options in doing these alternative functions.